So I have an exercise from section 4.3. I'll bring it up on the screen here so you can see it and read it with me. It's about getting a colonoscopy to screen for colon cancer. And this one is interesting to me because I had an uncle who died very young from colon cancer. So because I have that in my family, I'm expected to get screened at an earlier age than most people. So let's see, this should be it here. All right, section, yeah, 4.3. Oh, nope, oh. Am I in the right section? I am not in the right section. It must be in section 4.2. I lied. It's problem 4.79. And if you haven't read through some of the problems in the book, there are some really interesting problems, more than we could ever go over in a quarter or a year. All right, here it is, the colonoscopy one. So I'm going to borrow this text. Notes so I can blow it up a little more. Bear with me. Come on. Okay, so hopefully that is readable, just to make sure. Blow it up again. All right, so colonoscopy is a screening test for colon cancer. Recommended as a routine test for adults over the age of 50. In one study, and the 21 is just their reference to the study, it's linked in the book, provides some evidence that this test saves lives. The proportion of people with colon polyps expected to die from colon cancer is about 1%, 0.01. A sample of 2,602 people who had polyps removed during a colonoscopy were followed for 20 years, and 12 of them died from colon cancer. We want to assess the strength of the evidence that the proportion of people who die from colon cancer after having polyps removed in a colonoscopy is less than the expected proportion without a colonoscopy. Okay, so this one is a little tricky because they're talking about all adults. They're talking about adults who had a colonoscopy. They're also talking about adults who had a colonoscopy with polyps. So we got to kind of figure out what is the population in question. So up front, they talk about, in general, the proportion of people with colon polyps expected to die of colon cancer is 0.01. So although they recommend all adults have a colonoscopy, that's to see if there's polyps. If you happen to have polyps, then there's a 1% chance that you will die of colon cancer because of those polyps. So polyps are just these little growths in your colon. They look like little tiny little fingers in there. They're not supposed to be there. They just happen for some reason. I don't know why. I'm not a doctor. So here I'm going to say the population is adults with colon polyps. I can't spell polyps. Better. Now, keep in mind, I sometimes will make these look easy, but I read this, I was just thumbing through the book to look at some problems to throw in today. And I have more than enough, but this one just caught my eye and I threw it in at the last minute. So before class, I had to read this several times to try and decide what's my population here. Is it all adults? Not exactly. Is it adults who had a colonoscopy? Not exactly. I think it narrows down to just adults with colon polyps. Now, we only know they have colon polyps if they have a colonoscopy, and that's kind of a whole nother issue. My parameter here, I guess I'll stick with green. And parameter, again, is a thing from the population, not from the sample. So the parameter is the proportion of adults with colon polyps died from colon cancer. This is a proportion, so it gets the symbol P, and this proportion is 0.01, which we could also think about as 1%. All right, and I'm kind of running out of room to write on this screen, so I'm just going to kind of abbreviate up here. My sample is this 2,602 people who were followed for 20 years. 12 of them over those 20 years died from colon cancer. So from the sample, I have this statistic. It's a sample proportion, so it gets the symbol p hat, and p hat is whatever 12 out of 26,002 is. And so I've identified my population, my sample, and my proportion. The next thing we identify is our null and alternative hypothesis. So let's look at that last sentence again. We want to assess the strength of the evidence that the proportion of people who die from colon cancer after having the polyps removed, right? So they do the colonoscopy, they say, oh, there's a polyp, snip, they take it out. And then they test that to see if it's cancerous. I mentioned my uncle died when he was 55 of colon cancer. So my doctor said at 40, you're going to get your first colonoscopy. So I had to have one at 40, and I had to have one at 45. I just had one at 50. I'm going to have another one at 55. And it's definitely worth it for me because there is some genetic component to colon cancer. All right, so is less than. Okay, so less than, that means that's our alternative hypothesis. So let's write that down, and then we'll run our test. So usually the next thing I do once I've identified my population parameter, sample, and statistic is I kind of draw a sketch. Oops, wrong way. There we go. And put in my hypotheses. So hypotheses, page 0. That's that the proportion is 0.01, 1%. Alternative, page A. That's that the proportion is hopefully less than that colon cancer screening helps with the colonoscopy. And then I start my sketch based on that. So I'll put the sketch over here. So I'm drawing a smooth version of what StatKey creates for me. And in the middle of that goes my null hypothesis. P is 0.01. Now I have this sample statistic, X bar, which we're about to figure out. That's 12 out of 2602. And I have not yet looked to see what that is. 12 over 2602, my calculator says that is 0046 if I went to 4 decimal places. 0.0046. So it's, I could round it to 3 decimal places. It's about 0.5% versus 1%. And the question is 0.5% significantly less than 1%? And the answer is, it depends on the situation. So let's see if this situation is this significantly less. Does it make enough of a difference getting a colonoscopy? It's a pretty invasive procedure. You got to take all these crazy drugs ahead of time, laxatives, and not eat for a day, and then they stick a camera up your butt, and you have to be anesthetized, and somebody's got to drive you around after because you talk nonsense for a day. So it's not that bad, but it ain't trivial. All right, StatKey time. So back to the StatKey homepage. This time we're going to go to randomization hypothesis test for a single proportion. And I will share that link with you in case you're having trouble getting there. So this is hypothesis test proportion. Excuse me, spelling there. Here's the link. Now, a proportion is a little easier to work with than a mean because you don't have to have all of the data. You just need the count and the total sample size. So here, when I go to edit data, I type my count, 12 people died out of 2,602 people who had colon polyps. And then StatKey will then calculate that number for me, and it rounded it to 0.0050. Interesting. So So when I typed it into my, so it's doing a slightly different rounding. Did I type mine right? 12 out of 2,602. Yeah, okay, I'm just gonna go with it. Slightly different rounding than I would expect since they have a place for a fourth decimal. So let's see, am I ready to go? I put my sample data in, what am I missing? The null hypothesis. So you gotta make sure you set that too. Null hypothesis, 0.01. It's always a decimal. And they tell me up here, hey, it's gotta be a decimal between 0 and 1. Okay. Okay, so my data's there, my null hypothesis is there. Generate, 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 generate. And let's go 7,000 again for fun. It's a nice number. All right, am I doing a left tail or a right tail? Okay, so go back to my picture and think about that for a sec. Let's see. My number here is definitely less than. It's out here, so that means I'm doing a left tail. So sorry, did I say null? Alternative hypothesis tells us which tail. Sorry if I misspoke there. So generated my sampling distribution, left tail, and then I plug in my number. 0.005 according to StatKey. And if you wanted to type the other version you calculated, like I calculated the 4.6, go for it. I doubt it'll yield much of a difference. So if I put my 0.046 in there, StatKey says, hey, there's about a 0.0023 chance of that. If I go with what StatKey said, 0.005, hit OK. Oh, it came out to be quite a bit different. All right. I like my version better, but my general procedure for this is to say just use the number StatKey gave you. So let's do that. So this is my p-value here. So now I got to put this into my sketch. So notice how far away the sample statistic is from the null hypothesis. I want that to be reflected in my sketch. And I want to indicate what the p-value is too. So somewhere out here-ish is my, not x bar. This is not a mean. This is a proportion, Gary. All right. This is p hat. P hat. And that's that 0.00. And I actually switched over to the StatKey version. They rounded to 3 decimal places. I'm going to adjust my notes to reflect them doing that. And StatKey calculates how many other samples out of the 7,000 I made ended up in this region right here. And StatKey said that's called a p-value. Now we got to have careful notation. P, that's the null hypothesis. P hat, that's the sample data. And then there's the p-value. Get a lot of p's floating around here. StatKey said it was 0.0046. As a percentage, we would move the decimal point twice, so that would be 0.46%. That's a pretty small percentage. That's way less than 5%. Right? So the usual significance level that's alpha. It's usually 0.005. Oops, sorry, I lied. 0.05 or 5%. Now, that's for like common things. Getting a colonoscopy is not common. It's not cheap. It's a pain in the butt, literally. And colon polyps can be a matter of life or death. So I'm going to say, you know, I think this is more important than 5%. I think I'm going to set the significance level at 1%. So then the question is, did my data end up with a result that's less likely than 1%? And the answer is, yeah, this is like a 0.5% chance of happening here. So is my p-value significant? Is my data significant when I'm expecting a 1% significance level? And the answer is, yeah, that's smaller. My p-value is 0.0046. The significance level alpha is 0.01, and I am definitely, my sample data is definitely less likely than that. So this says reject the null hypothesis. If you reject the null, that means you have evidence supporting the alternative. Then, there we go. Supporting alternative. What's the alternative? The alternative is that the proportion of people who die from colon polyps is about 1%. And so we think if they got a colonoscopy and those polyps were removed, they're less likely to die, which is a big deal. Okay. So this is my decision. I am deciding to reject the null hypothesis. So then I state my conclusion. And so my conclusion is just kind of goes back to the question that was asked here. We want to assess the strength of the evidence that the proportion of people who die from colon cancer after having polyps removed in a colonoscopy is less than the expected proportion of 1%. Did we find evidence that the proportion is less than 1%? The answer is we did. We did. So this sample proportion is strong evidence. Strong because it's lower than my significance level. Strong evidence that, let's see, I don't want to word that, that's a complicated question. And again, whenever you're struggling to state in words, like make a press release about what does this mean, usually the kind of the question that was asked, kind of restate it instead of as a question, as a statement. Yes, we have evidence of this. So evidence that the proportion of people who die from colon cancer after having polyps removed in a colonoscopy is less than 1%. Okay, there it is. That so we just restate that. Proportion of people who die from colon cancer after having polyps removed. So sometimes it gets a little wordy. After having polyps removed in a colonoscopy. In a colonoscopy. Is less than 1%. So the big idea here is StatKey runs the test for us when we push the buttons in the right order. Once we get that to happen, then we have to make a decision. Okay, does this give me evidence toward the alternative hypothesis? Either it does or it doesn't. Okay, in this case, it did. I got a pretty small p-value. So p-value is that number of other samples that had something, in this case, less than, could be more than. If that's the case, then we reject the null, and then we got to state what it means to reject the null and show that we have evidence of the alternative hypothesis. And so we're just going to keep doing some more examples of this. But we've been going at this strong for an hour. Let's take a brief break.